Welcome back to another stream. Last time we triumphantly left off in a place where we had a working Pokemon playing AI. This time we are taking the next steps to make that AI much better, because last time where we left off it was making all sorts of dumb decisions. It wasn't really able to score effectively any of the moves that we were telling it to use very well. And so now what we're going to do is we're going to take this stream to improve the model and make it as good as possible so that it's actually a competent model. So right now, the best it should be able to do is learn from what good things happened in random and to be able to predict how good different moves are given the random results. Unfortunately, that data is very imbalanced. There's a lot more bad or just neutral moves than there are good moves. So we need to figure out a way of making the model see some of the good insights from it, and at least just slightly better. This is improving the neural network, or whatever machine learning model part of it exists. So the first half of the stream will just be architecting different models that we can use, and then the second half will be creating the framework for the reinforcement learning that will improve that model, because it's kind of two phases. One phase is the actual simulation training of a model, which we just want to give us a baseline model. And the second part is reinforcement learning, to take the trained model and improve it, make it even better. So that's kind of what we'll be doing today. And it'll be another long stream, but it should just be one stream to get this stuff done, at least working in a way that we are at least minimally satisfied with it. So without further ado, let's jump into it. Let's get started. So what we've got from last time is some training data based off of our million battle simulation. So this is a huge amount of data that's been created by a bunch of random battlers that just pick random moves each time. And in fact, we've simulated 1 million battles. This is a very, very, very large amount of data, so we can train very deep neural networks off this data. Currently, what this script is doing in the background is this is just cleaning up some of the data to make it in a more user-friendly way, so that whatever model we train can easily do it. I've made some tweaks to how the data works in the background, so that's why this is running right now, but we should have at least enough to play around with. It's very small, but it's on batch 34 out of 500, and each of those batches has 100,000 rows of data. So we've already got 3.4 million rows of data that we can play around with for starters. So let's dive into that. I think the first thing that we'll do is try some alternate approaches compared to neural networks to see how they do as a baseline. And then we'll compare against our current neural network model, which is slow to train, but has the potential to do very well based off this large amount of data we have. Traditional machine learning methods do not require large amounts of data, but have kind of a ceiling. So we'll see. And what we can do is we're going to create a new Jupyter Notebook. I'm going to spread this window out just a little bit more. That way the code's on the left, my face is right here on the right corner, and chat will show up in the bottom right corner. Great. So what I want to do is I want to try out this library called TensorFlow Decision Forests. Supposedly decision forests are a great way of dealing with a large amount of columns in your data set. So we'll put that to the test and see exactly if that helps. Let's zoom in a little bit on the notebook. And let's install that library. So I'm going to zoom in just a little bit more. So I'm going to say pip install. I'm just going to copy this. TensorFlow Decision Forests. This is going to install that library in the background. Oh, could not. No matching library. Is this not a thing that exists? Maybe we can add the upgrade? I don't think that would matter though. I just copy pasted it directly. Is there a different version of this that I'm not aware of? Oh, it's not available for Mac or Windows. Nice. Well, we can just use a different decision forest framework. That's why. Great. Okay, so quick change of plans. We'll just use a different library for decision forests. So how about, I think sklearn, like scikit-learn, has decision forest support. Random forest regressor. So we're going to say from sklearn.ensemble import random forest regressor. We're also going to say import pandas as PD and import plotly.express as px. That way plotly is for visuals and pandas is just for data loading and things like that, and our random forest regressor will be for training a random forest regressor. So, another thing that we need to do is we need to say from glob import glob, and just because it might matter, we're going to say from tqdm import tqdm. Glob is for finding files, and tqdm is for progress bars. So let's pull, for now, 10 files. So this will be 1,000,000 rows of data at once. So what we're going to do is we're going to say something like df list equals that, and we're going to say for f in glob my files are at u/programming /simulation data /star.feather, and I'm going to go ahead and have that be a sorted list just in case, because I'm not sure if it sorts it, but may as well. And actually, I'm just going to take the first 10 items for now. That's 1,000,000 rows of data. That should be enough to kind of give us an indication of what's going on. We're going to say df is equal to pd.readFeather f. And then what we're going to do is we're just going to say df list.append df. And lastly, we're going to say df is equal to pd.concat df list ignore index equals true. And see this work. This might take a few moments because I'm pretty sure reading each feather file takes about like 5 to 10 seconds or so. So this might take like 2 minutes to run. In the meantime, let me edit my stream info. There we go. Alright, and at the same time as editing the stream info, we've got our data loaded. So you can see it's got 1,000,000 rows with 11,000 columns. So there's a very, very large amount of columns. All of our input values are all of these columns to the left. There's lots and lots and lots of them. And then our output columns are the game score, which can be any number, positive or negative, any real number. So now let's use this random forest regressor basically out of the box to see if we can get it working. We'll switch to more sophisticated methods later, but for now, random forest may as well. So we'll do this regressor. So let's go over here. We're going to say, we're just going to copy paste exactly. Instead of max depth being 2, what's the default max depth? We can play around with increasing it and decreasing it. Max depth is typically, I didn't see max, oh, right there. Default is none. Okay, we'll just leave it not specified then for now. We will give it a random state for repeatability. Otherwise, I think for now that's fine. And we're also going to watch our memory usage, which has jumped up to 164 gigs from us loading this in this million rows of data. So we'll make sure that it's not too bad. But what we need to do is we need to say that x is going to be equal to df.iloc, which just selects an integer range of columns. We're going to get every row and every column except for the last one. And then y is going to be just df.iloc every row and then only the last one. Now we can just say regressor.fit x, y, but let's make sure that there is some amount of progress that can be shown, because otherwise we'll have no idea if this is just taking forever or what's going on. Unfortunately, I don't think there are any ways we can get progress by default. Let's see if there is. sklearn random forest fit progress. It's when creating the random classifier. There's a verbose keyword, or there may not be. Verbose. Okay, so we just need to say verbose equals 1. There we go. And let's see if this works. So our memory usage has dropped a little bit just because our data wasn't really doing anything. But it's just sitting here for a little bit. Okay, and now we've got parallel usage. I'm gonna put this over here. So it's just behind chat, but it's pretty clear what's going on with the memory usage. Is there CPU usage? Yep, seems like it. None means 1, so we should probably give it the ability to use multiple threads, otherwise it's going to take forever. So let's specify what would be good. This is a 24 core CPU, which means it can have up to 48 threads, so I'm going to go ahead and say n jobs is equal to 20. That should be a good amount of threads to run at once. And you can see that our memory dropped whenever we restarted the Jupyter Notebook, and it'll climb back up to that huge amount of memory very quickly. I guess I could add a TQDM thing here. That way in the future, whenever we're reading the data, it's a progress bar. But I don't think it really matters too much, so. Okay, now we're using 20 jobs in the backend. So it's using backend threading backend with 20 concurrent workers. And our CPU usage has definitely increased on the computer. So I'm going to go ahead and turn on the air conditioning in here because this room could get hot pretty soon. And that would not be too fun. Okay, so it's started at least. I was hoping that the verboseness would show us a progress bar, but it's not really telling us too much information. We might want to start with a smaller amount of data. I would say I'm decent enough. I have a job where my entire job is doing machine learning. So it's definitely good enough to have a job. I'm not as focused on the statistical based methods, so I'm not the best with the actual kind of statistics for traditional methods. My focus is mostly on deep learning. But yeah, I know a decent amount, more or less, about machine learning. Yeah, I've built a neural network from scratch before. Using from scratch meaning like NumPy in Python. I've never done it not using NumPy, but that's kind of crazy not to use NumPy. You could do it with for loops, but it would take hundreds of times longer to train compared to using like NumPy. But yeah, right now, since our data is suffering from the large P compared to N problem, neural networks aren't the best for that. So I think today we're going to tackle a couple of different things. I've never implemented SVD from scratch or anything like that. That's singular value decomposition or something, right? SVD. Singular value decomposition, yeah. I've never done it from scratch myself. For singular value decomposition, I've done something similar for like a numerical methods class. Like I did like in college. It wasn't SVD, it was some other matrix decomposition. It might have been like special cases like diagonal or symmetric matrix decomposition. I guess for most advanced, I've used transformer models for language translation. Yeah, I think it's not going to give us progress because it's clearly working on something, but it's just not telling us how it's doing, which is annoying. But transformer models are pretty state-of-the-art for machine translation. Like they're pretty complicated things. For like, I guess a unique subject, like I guess that's kind of a vague question. I'm not really sure what you mean, but I guess for me the most unique thing that I've done in machine learning, or the most niche things that I've done in machine learning, has been large-scale data sets for machine translation models. I got really into like a couple months ago, really doing like high-end model training for language translation. And I got to the point where I knew the state of the art. Like I read all the papers for the modern approaches to transformers and the things where there are no Python libraries that do everything. So like reformer models are an alternative to transformer models that you can, in theory, train on one GPU. So I found a library for doing reformer models that wasn't really working too well, and I took it on my own and got it working. And yeah, like I know what you mean. I prefer sequential models for machine translation, but I can't deny the performance of transformers. But like it does become something that I'm not really able to do at home. Like I have a decent machine. Like you can see I've got lots and lots of cores and a huge amount of memory, but training a transformer model would be beyond the scope of what I can do on this machine. Even a small transformer model, it would not fit on the GPU on this machine. I would need multiple GPUs, probably several GPUs, in order to try to train something like that. So I get what you mean, especially with it not being similar to humans. Okay, I'm gonna stop this early just to see if I can get this on a smaller dataset rather than 1,000,000 rows right off the bat. Time it on 100,000 rows and see if it's something that's wrong or what is the problem causing. I haven't seen binary neural networks. I haven't dived too deeply into the kind of underlying architectures of a lot of like kind of redoing the neural network stuff, but I think it is something that would be interesting to do. Okay, I'm just gonna do one file now. So this is 100,000 rows, and see if the speed compared to this is better. At least with neural networks, there's some indication of the progress in training. This doesn't seem to give us anything. No indication of what's going on. I'm actually in school for a master's degree right now. I'm taking one online. Not a very good set of courses. Like if you're trying to learn machine learning, I kind of don't recommend doing a master's, because unless you go to a nice school, I don't think what you would learn in the classes there is even on the same level as free courses available on the internet. Like the course that I'm in right now, the most recent paper that we've had to read, and the course is almost over, is from 10 years ago at this point. And this is a graduate level course about machine learning. So I'm getting a master's degree. I'm mostly just doing it for the paper. I currently work in Japan, and they do not have a lot of AI people here, it seems, because there is a lot of available jobs for AI, and it is easy to get your foot in the door with not a lot of qualifications. I've still worked in machine learning for like 3 years now, and I just recently started a new job leveraging that previous work experience. So I don't want to make it seem like I don't know what I'm doing or I don't have much experience, but a lot of places in the US, for example, like require a master's degree, or minimum is a PhD, or minimum is a master's, recommended is PhD. So Japan, there's a huge job market for AI jobs, machine learning jobs, even if you don't speak Japanese, because I don't speak Japanese. Yeah, I've heard that too. Like Japan is a fan of fuzzy logic. My toothbrush claims to use AI in it, and it probably means fuzzy logic. I think it's for sensitivity, that like if you push too strong, then it's it like beeps at you because you're brushing too hard, and if you do it not enough, then it also beeps at you because you're not doing enough pressure. I don't know. Like our laundry machine has AI in it, but like all of these things are sensor-based fuzzy logic, which is basically just setting thresholds, and if you exceed a threshold, to increase your pedal in the other direction. But yeah, I do not know what's taking it so long. My guess is just it's because of the 11,000 columns. Maybe I should set a max depth too, because otherwise it's going to be a lot of columns potentially, so, or a very deep model potentially. The weird thing is my memory usage is very, oh yeah, because I just switched it down to one file, no wonder. You know, part of me wants to be patient and just see how long this takes, but it's kind of annoying. We have trained a neural network to do exactly what we're trying to do right now, but the issue is that it's basically predicting 0. And what that means is that the model is kind of getting stuck in this local minimum, or local minimum of error, where basically the best thing the model can do is just predict 0 for everything. And since this is a regression problem with mean approximately 0 and a very normal distribution, that's not a bad idea for the model to do. Like if I show a histogram of what the actual data looks like let's make another line. Let's do px dot histogram x equals game score. We can see that the data is very centralized to 0, and a lot of the rows are very close to 0. So what that does is there is clearly a local minimum if you predict everything to be 0. So, and with 11,000 columns, it seems like our initialization is not doing a good job at helping us escape this local minimum. So what it's basically doing is just saying, okay, everything has weight 0, or everything has a game score of 0. And when you do that, your average mean squared error is about 1,000 in this case. For this data, your average mean squared error, if you just always guess 0, is about 1,000. And well, if we look at our training history, we see that the validation loss, the training loss, is just under 1,000. So that's likely what's happening. It could be something different, but it's very suspicious that the mean squared error of this data, if we guessed 0 all the time, is about 1,000, and this is about 1,000. So it could be something that it would just take days to train to kind of get out of that minimum, and we'd have to do some kind of advanced learning rate scheduling to get it out of there. So if we can find a better out-of-the-box approach, then that would be great. And that's a very strong if, because at this rate, this is taking forever to even just give us any indication of what's going on. I'm going to try changing the max depth to 2, just like we saw before. And now this should give us horrible performance, but I just want to see what is causing this to take so long. Because if it does just take this long, then that's kind of not usable. Alright, we've restarted this, and now let's go back to max depth. So let's say max depth, we're going to say max depth equals 5. So at each thing in the random forest, we should see up to 5 branches, and for the number at once, which is n estimators, I'm going to use 10 n estimators. N estimators is equal to 10. Oh, very slow. I'm really bad at typing for some reason. I don't know why. I'm just a very slow typer. While this is running, I guess I could even time it. What's that website for testing time? Typing.io. Okay. Typing practice for programmers. Oh, I'm probably gonna be even worse with this. Okay, let's try Python. Python Mercurial. 465 lines. That's a lot of lines. Do C? Psh, I'm not good at C. I'm like I would rather do a language that at least I'm vaguely familiar with it. All right, does it start timing me as soon as I start writing? Oh, all right. Let's see. Class. I'm so bad. Okay, that was awful. That was miserable. Let's see. Word per minute 41. Yeah, that was bad. So I'm not a fast typer. I don't know what it is. Like I spend all the time on a computer, but I'm just never good at it. Okay, there we go. So setting a maximum for the max depth helped a lot. What about as for how good did it do? The score to beat from a mean squared error perspective is 1,000, basically. We just want to see is it doing at least better. So let's just say dot predict x. So this is going to be y hat. And then what we're going to do is we're going to say y minus y hat squared dot mean. Let's see. 924. Okay, so Random Forest is already showing that it's better at dealing with this kind of data than our out-of-the-shelf neural network. And the reason is that there are 11,000 columns of data that we have for this Pokemon predicting AI. And Random Forest can kind of deal with that insane amount of data. It seems the whole thing took like a minute to run. So now we can kind of step up some of the stats because we really limited it. So we can send it back up to 100 estimators and see, for one, does it take 5 times as long? Yeah, Random Forest is a little bit of a weird name, but I think the next thing that I'll do is maybe like gradient boosted forests, so then at least the name isn't too bad. But yeah, I did not do well for typing. Okay, so we've got this Random Forest regressor. What other things do we have for regressors? We've got gradient boosting regressor that we can try out. That's kind of a little mix of some, gradient style learning with this. So maybe it'll kind of give us a best of both worlds. That would be really nice if we could have that. Oh, and by default, it supports Quantile, which could help us for our style of learning that we're doing. Okay, so it just says done 10 tasks. But are there 100 tasks? Is that how this works? Because there's 100 estimators, there's 100 tasks? CPU still being hit pretty hard. One thing we can also do, because random forests and other kinds of more statistical based approaches to machine learning, they don't actually benefit from having huge data sets. You get really diminishing returns, whereas unlike in deep learning where you basically don't get diminishing returns, not for a long time in terms of data. Like you can almost always increase the size and increase your data and get more performance. That kind of stops with these kinds of models, and the time also doesn't grow linearly. So what we could do is we could just try to construct a good training data set where the histogram isn't so imbalanced. We can kind of get rid of some of these cases almost randomly so that it doesn't overfit to these random cases so much. Now, decision forests, they don't typically have the same kinds of problems. It's a little bit of a different thing. I don't know why the progress doesn't really work on Jupyter Notebooks. Maybe it's a Jupyter Notebooks thing. Because we just did not really get progress for that. That was kind of annoying. Okay, so stepping it up to 100 estimators decreased our loss by a little bit. And this is lower than 1,000, which is nice. The whole thing took about 3 minutes. So let's say instead of max depth being 10, let's step it up to 20. Or instead of max depth being 5, let's step it up to 20. So this will make a lot more trees, or a lot more deep trees in our network, and that could make use of a lot more of these columns. Because at each split in a tree, it's looking at one column, typically. Like the way that it works is that you are checking one column for some sort of threshold. If it's greater than this, you do this. If it's less than this, you do that, etc. So one thing that we might want to do is kind of construct a data set that has a good mixture of all the different row values and column values that you would see, including some of the ones that are very rare, that have very high game scores or very low game scores, so that it can kind of learn a little bit about those. That's something that would kind of be worth doing if these models seem like the way to go. And so far, at least, it's seeming like it's not too bad of an idea. Okay, while it's running, let's make fun of how bad I am at typing again. So what's it? Monkey type? monkeytype.com. Alright, so this is normal text. Maybe I'll be faster with normal text. Let's see. Okay, I'm still a very slow typer. Word per minute 63. So I'm 50% faster at typing just normal words than I am at typing Python code, but I'm just a very slow typer. I don't know what it is. I've typed all my life. But Yeah, the highest I ever went was like 80. 84, which is still pretty slow. Okay, so this clearly is showing a larger amount of time to run. The last one did 10 tasks in 27 seconds and finished the whole thing in like 2.7 minutes. This one did 10 tasks in 2.5 minutes and is taking much longer. Unfortunately, these things are all CPU bound. There's no getting effort out of our GPU for this. All of this GPU work is just the streaming. So we're not really making use of the hardware too much. At least now the CPU is getting a workout. But that would be a way of optimizing how this is working. And also, because it might not be so clear, what the model is actually trying to predict right now is, given a set of observations and a move to use in this set of observations, what is the predicted outcome, or what is the predicted score of this turn? And that predicted score is kind of a function of two different things. It's a function of what is going on right now, and like with the opponents and you and everything, how well did that move work out? And then it's weighted a little bit by how much did the game overall work. Because maybe some moves are generally decent at the same time, but one leads to you winning earlier versus later, so it would get kind of retroactively boosted a little bit in terms of score. So it is a little bit unfair to the model because it doesn't get to know the whole history and what happens in the future to be able to score. And maybe the opponent just gets really lucky. So we shouldn't expect it to have 0 mean squared error. That would be overfitting to the data. So instead, we just kind of want it to be good enough, and by good enough, we just mean it kind of makes sense, and it kind of works. So we've already written all of the code to do showdown battles based off of one of these models, and it's pretty plug and play. So once any of these models train and show better results, what we'll do is we'll just export the model, boot up Pokemon Showdown, and do some challenge matches against it. So if that's something you're interested in, trying out your hand at playing against the AI that we're training right here in Pokemon Showdown, that's something that we'll be doing off and on today as we get results in this. As it takes time to run. My CPU is only at 67% load, so I could probably step it up in terms of jobs, but we can see that these are the 4 cores down here that aren't really getting hit, and it's doing 20 jobs on everything else. Hey, welcome to the stream again. We're working on an AI to beat or to play Pokemon. Last time we got something working using a neural network, but the issue with neural networks is they don't really work too well when there's a lot of columns, and we have a lot of columns. So we're trying out some methods that in theory can deal with that much easier, and this is one of them, and we're already seeing better results. So I've been doing pretty well, and I'm hopeful that some of these will show some better results. And we've got everything set up, so as soon as a model is trained, we can immediately try it out in real Pokemon Showdown, and you can play against it even. Like, it's all hooked up so that over the internet it can play. We just have to export the model and load it, and 10 minutes later we can be in a game. So this is just running. Hopefully it'll finish up this round of training, and we can see if stepping up the parameters in this way helped. And we'll also try this gradient boosting regressor. Despite myself, I'm a data scientist at a company, and I do machine learning stuff. I really haven't done a whole lot with your more traditional statistics-based machine learning methods. So hopefully I'll be able to like do these pretty easily and get things working, but I don't really know. Like I don't know all of like the best ways of getting these things to work. Like I don't know if voting regressors or histogram gradient boosting regressors or anything like that are the best. Yeah, exactly, in Japan. But hopefully I'll learn more through doing stuff like this. Like, I most of my familiarity is in neural networks. Like, I know all sorts of different architectures and all of that. Yeah, also earlier while we were waiting for things to run, I've been humiliated in my typing speed on 2 different typing websites, both typing.io and monkeytype.com, where I showed off my stunning 63 words per minute, which is not too great for that. Yeah, recurrent neural networks. I like lots of sequence-based machine translation involves recurrent neural networks. Specifically, LSTMs are the common thing for that. So I know a lot about LSTMs, the architecture. I could draw a full LSTM cell, but maybe not on command. Like, don't call me on it. But I've never built my own RNN, but I've at least been able to kind of diagram it, and I know how it works with the kind of, you know, recurrent gate and the input gate and those things, especially, and then also with like more advanced things like LSTMs. Yeah, actually, while this is running, in that case, let's talk about LSTMs. This is not relevant to the project, but hey, why not? Let's make sure it's recording. So the idea for LSTMs, and it's not that much more complicated than a recurrent neural network. So if you know recurrent neural networks, as long as you kind of keep yourself general in your mind and not worry about too much of the fine details, it's not that much worse. So your idea is that your input data is some sort of sequence. In this case, I'm going to assume it's like language translation, just because it's easy to draw. So if you had some word like input, the idea is if we were doing like a character-based machine translation model, each input is actually just one letter at a time. So first, the I is passed in, which is actually some one-hot encoding or integer or whatever, but in this case, I'm just going to draw an arrow directly showing the I going into the model. In practice, you've got all sorts of abstractions that you would do for categorical variables. And the idea is that it goes into this LSTM cell, or recurrent cell, that at the beginning is just remembering basically a blank slate of zeros. Yeah, exactly. So basically, at the beginning, it has no memory. It's just reading in some zeros for the memory. What it's going to do is it's going to do a couple of different operations. I'm not going to draw all of the actual operations with what happens and like the activation functions like the tanh and whatever, but essentially, so right now what I'm drawing is a recurrent, like just a simple RNN cell, and then I'll mention the difference about a LSTM. So basically what happens is that these two vectors are used in a function to then determine two different output vectors. So for now, this is all still a black box. This is still just a mystery. How does it work? What's important is that there are two inputs and two outputs. The input down here, this is the actual input, like you're feeding it like an input string. So this is what we're going to name our actual input layer. This is the memory, typically denoted C, for context. So what it's going to do after one running of the cell is it's going to somehow use this memory and this input vector to spit out two things. It's going to spit out an output and it's going to spit out a memory. This time, the memory will be altered in some way based off of what has happened. And then the next character will be fed in. But now, instead of the memory being a vector of zeros, like we initialized it with, the vector is whatever the first running output. So then we have this black box again. It outputs a new output. And to the right, it outputs memory. And so on and so forth. Now, as for what is actually happening inside one of those, what goes on is like, and actually, you say it's a lot of cells. The secret is there's actually only one cell. It's the same cell that gets used over and over and over again. So you can't do it in parallel. That's an important limitation about sequential models, and it's why things like transformers exist, because transformers can work in parallel. But this is sequential. It goes first character, second character, third character, all into the same cell. So we've drawn it as multiple boxes here, but in reality, the real picture is more like there's one cell where at the start we pass in a bunch of zeros. Otherwise, we pass in the input and the memory goes back into it. And we go one at a time. Input, output, input, output. So this is typically called the rolled form. If you're taking like a course about sequential learning. And this is the unrolled form. I prefer the unrolled form as long as you remember that each of these black boxes is exactly the same black box. So if you have a certain set of weights, it's the same weights for all of them. Now, we've just kind of made it a black box for now. And I think the most important thing in neural networks, when you're doing neural networks, is to allow yourself to think of things in black boxes when you need to. And you can basically use and implement, using TensorFlow and Keras and all that type of things, a RNN just knowing this, with the black boxes and everything. You could then use it and know what's going on. So knowing when to allow yourself to just use black boxes is important. But let's dive deeper into two different things. So the first one is going to be what's in a simple plain old RNN. And the idea of what's in a plain old RNN is this. So what we do is we have our box. This time I'm going to draw it bigger. And we've got the memory, which I'm going to call the context, C. We've got our input, and first we add them. So this is the input vector, which I'm still calling I. Then it goes through some sort of activation, which typically is denoted as a fancy F. And then typically there is some sort of final activation based off of a bias layer or something, which will then output the output layer and output the memory. And this memory is then the new memory for the next time you run it. It's a bit like having a for loop in a neural network. Oh, oops. Let me move this over here and then drag this way. So that's the whole picture. For LSTMs, I typically use TensorFlow and Keras. TensorFlow and like Keras has a built-in LSTM thing. Yeah, I use Windows. I have more and more reason every day to switch to Linux, but then I just find some sort of proprietary tool that only works on Windows, and then it's just like, well, do I want to get a Windows virtual machine? And then Windows doesn't play well with virtual machines. I have a MacBook as well, so I use that for some things, but if I were to switch OSs on this, I'd switch to Linux, just because I built this machine up. So that's the idea of an RNN cell. And again, the idea is, pretty simple. It's just trying to use this extra vector that is not being input. Yeah, I have an old MacBook. It's like a 2015 MacBook Pro. And then technically my work laptop is a MacBook. It's one of the new M1 Pro MacBooks, but I wouldn't really consider that my laptop. It's my work laptop. Oh, I guess I should probably check on the model running. Oh, it finished. Okay, yeah, and wow, 697. Significantly lower. Yeah, no, Japan does not pay 40K for ML. It doesn't pay nearly as much in the US, but I'll say that my salary is at least double that. So, it is more. For your typical software developer, though, that's normal. Like 40K for a typical software developer is actually normal in Japan, though. The job postings and the discussions that I had when I was looking for a new job, the range was 80 to 100 for somebody with about my experience, which is like 3 years of experience. So 3 years of machine learning experience. It depended on the place and what it was. And so yeah, I'll just say my personal salary, including the benefits with what I got, is double that. More than double that. So yeah, it's pretty neat. I moved here right before COVID hit though, so I haven't really done a huge amount. And no, I don't have a car. I just take the train everywhere, and that's basically enough, because why not? We were thinking about getting a car, but Okay, so the model is doing much better. 697, that's about 2/3 the mean squared error that was happening before. So we can keep running this in the background, but I'm going to step down the number of jobs, actually. I'm going to step it down to 10 jobs so that it only uses 10 cores. That way, and with a max depth of maybe deeper or something, or what other things can we change about this in our random forest regressor? Yeah, actually, that kind of middle layer basically between hardware and virtual machines. I know a little bit about software virtualization, but not nearly enough to make it a job or anything. I just know the basics. So, but I'm at least enough to know what a hypervisor is. Like, I probably couldn't tell you how they work at a fundamental level, but I have installed a hypervisor once to a machine and then installed VMs on top of it in a usage capacity. I've done that at least. Yeah, I'm the exact opposite basically. I prefer the areas where we can be as wasteful as we want with memory, and just, if the problem is that we're running out of resources, just go and pay more to AWS so we can get more resources. So I'm the exact opposite. I'm like low efficiency type of software developer. Yeah, like I use NumPy all the time. In fact, Pandas, which I use all the time, is based off of NumPy. But a lot of the kind of faster, more efficient code that I'll write in Python uses NumPy. And I know NumPy uses C in the backend. Yeah, like, I mean, for my mindset, I'm very functional in mindset. So, like, I don't mind the kind of quirks that Python has regarding that. But yeah, I know it is weird, especially for people who are used to more machine-related libraries or machine-compiled libraries compared to Python, which is a little bit more abstract. Yeah, like I've gotten to the point though that I'm kind of spoiled on Python, and now it's too late. I can't go and do anything else. So I'm gonna do something with a max depth of 50 now. The whole thing took 12 minutes to run, so if we a little over double it again, then that could take like 30 minutes to run. But in the meantime, we'll just leave it, and we'll create a new notebook to test out one of the other trees. So I'm going to go ahead and duplicate this notebook. Move that right there. Alright, and then this one is going to be for, I guess, maybe the gradient boosting regressor. Why not? And we'll see how that performs in comparison. Alright, so random seed is not going to stay the same across these. Like, it's not going to be so useful, but we'll keep the random seed in place. I'm basically just a Python programmer. I mean, I've done a little bit of C++ when I've had to, but I'm not the best at it. And obviously things like SQL and those types of things. But I'm just, I'm much more specialized than I am supportive of a bunch of different languages. And I mean, yeah, I think it just entirely depends on what you're doing, though. Because one thing I will say is that when you're applying to jobs, at least, if you list a lot, sometimes people will think that you're just listing a lot to list a lot, and that you don't actually know it. So it's probably, if you're wording it on a resume, you basically just, it's more helpful, instead of having a languages section where you know a bunch of languages, you have a projects section, and you say, I did this project in C++, I did this project in Java, I worked at this job and I did Python. Like, if you list what language you did in like a kind of more project-based, then it's like, okay, yeah, this person knows what they're talking about, because they're showing that they did things in those different languages. Yeah, it's kind of like the master one and working on multiple kind of thing. But the other risk is that if you have a lot and you say that you know a lot, people might interpret it as you actually just know a couple and you're listing everything you've ever seen a tutorial on the internet for. And that's less helpful. But I think it just depends on what you're doing. If you're not doing this for a resume, then it's, yeah, you can say you know whatever you want. Alright, I'm just going to stick with the defaults, or basically the same ones for random forest in gradient boosting. So basically the same parameters, and let's just see how it goes. I'm sure it'll still be slow, but I'm going to do 20 for max depth because that's what we were just comparing it against. And the score to beat was like 620, or no, 690. So we'll see if it actually helped. Oh, end jobs. Oh, is gradient boosting regressor not something that is parallelizable? Because it says end jobs is not a thing that it accepts. I would disagree with the pretty useless for real apps. I think it absolutely depends on what you're doing. Because you can, like, as long as you're leveraging performant libraries on the back end, the overhead of using Python and interpreted languages is very small in practice. So it's, like, especially from a development time perspective, if you're trying to create a model and even deploy a model to production, the support is not something you can really ignore when considering a language's efficiency. C might run 1,000 times faster, but it might take you 1,000 times as long to write your code in. But, So maybe there isn't an end jobs thing. That might be bad. But I'll just get rid of it and see. Gradient boosting regressor, sklearn, parallel. Okay, so like using like XGBoost. I mean, I'd like to see it if it happens. I know that Python is becoming a lot more, or not Python, machine learning is becoming a lot more manageable from a tutorial level, but the flexibility of knowing a language that's practically pseudocode kind of helps. Because there are like drag and drop approaches to machine learning. But it's just, like, the flexibility isn't there. And yeah, interviews, like, all the interviews that I had where they actually had some sort of programming test, it was on a website where you could pick any language, and they said just pick whatever language. For me, the things that I had in my kind of interviews, were, like, programming assignments. Okay, but Python has NumPy. Like, that's what I mean, is that just like if you were talking about JavaScript, you can say JavaScript has, doesn't have some sort of support for something, but they have all the libraries and, node package management and whatever else that you can install. Python has NumPy, which you can install. There's no, like, nobody uses pure Python. Like, that's what I mean, is that, it doesn't matter at the end, because the answer to that is just install NumPy. So, who cares? From a practical perspective. I'm sure for a, company like Google, where massive amounts of their development is, running currently, and they need to squeeze out every bit of performance they can get, it's worth it. But Google runs TensorFlow, and TensorFlow's main supported language is Python. Like, the TensorFlow build for Python has the most features compared to the other languages. And that's Google's product. So, I mean, it is still, something there. There is, but not all of the feature sets exist for every language, and that's kind of one of the rough bits. Is that Like I had a project a while back where we were wanting to use TensorFlow compiled in C# for something. It was like to embed TensorFlow into a .NET application, but the feature set was just not there. Especially with the migration to TensorFlow 2, a lot of things were not supported right off the bat. But yeah, like this is, TensorFlow is Google's product, or at least Google contributes a lot to the project of TensorFlow. I don't know if it was always that way. I don't really know the history of it, but yeah, and like TensorFlow's main supported language is Python. Like, I don't even know if it shows it on their main TensorFlow website if you can get to C++ TensorFlow. Okay. Yeah, you have to go into the language bindings section to find out how to install it for other languages. So that's what I mean. Like, I think their idea is they'll probably... And this is for C, not even C++. But they also do a Java and Go on their main thing. But otherwise, it's Python. And I don't mean that the whole library is written in Python. TensorFlow on its backend is absolutely run in C++ or C or whatever. Right? Like, it's the scripts that it is being, and the languages that it's being compiled back down to in the backend are those efficient libraries. The part that's written in Python is the user face to using TensorFlow. But when you execute a graph of a TensorFlow network, it's being executed in an efficient language like C++. I'm not sure exactly what it is. It's probably, I would guess, C. But yeah. Okay, yeah. So already with our gradient boosting regression, after 2 iterations, we can see that the training loss is improving. Yeah, I think, like, if I remember correctly, Tesla sponsor TensorFlow C#. This was a few years ago, so maybe it never went anywhere. But I thought I remembered Tesla was wanting to sponsor TensorFlow to do C#, but then they didn't. Like, it was a long time ago, so I don't know if I can find something about it. I don't really know. Is GitHub down? I can still access my GitHub. Yeah, like, I've used PyTorch for something before, but I tend to stick to one ecosystem just because switching back and forth is annoying. Especially with CUDA. And now, like, this is annoying, right? Like, this is a Windows issue, or it's your development library issue, whatever. But the latest versions of TensorFlow and the latest versions of PyTorch do not use the same version of CUDA. Which means if you want both, you need to install a bunch of different versions of CUDA. Because one will use one and one will use the other. But you also have to be careful while you're installing it, because you don't want to install them in such a way that overwrites required libraries and breaks everything. And for whatever reason, in order to install it through pip instead of conda, you need to go through like a specific repository. It's annoying. Just do everything on pip. I hate conda. I don't like conda at all. I do everything through pip. It's the way to do things. But you have to like install specific versions of the wheel. I guess the problem doesn't exist from here in Japan. I don't know. Okay, the training loss is still dropping. I guess, and this is in minutes, right? Like remaining time. But I guess, I mean, it is working much better than the neural network approach, which is kind of annoying because I'm typically on team neural network. But it might be just because of all of the columns. So a third thing we could do, instead of this gradient boosting or the random forest approach, a third thing is we could do principal component analysis to reduce our columns, because odds are many of these columns have practically no impact on the output. Now, unfortunately, the issue at hand is that some of the principal components of this, or some of the columns of this, not principal components, some of the columns are important, but only in very niche circumstances. Which means that, for example, in the context of Pokemon, which is what we're doing, by the way, we're training this for Pokemon, whether or not the opponent is poisoned matters for certain moves to use, because some moves do more damage if the opponent's poisoned. Whereas for other things, the opponent being poisoned might not matter at all for calculating how good a move is. So the chance of that showing up in our raw data is probably pretty slim, and which means that doing principal component analysis could be a little bit difficult. And yeah, so I've done PCA before. I've never really done the other one. I've never pronounced it either. TSNE. Distributed stochastic neighbor embedding. I've seen it written, but I've never seen what it stands for. I've done it like in a course for something. So this is something that we could absolutely take a look at. A similar idea. I'll go in order. One-shot learning? Yes, that's what our neural network is doing for this problem, actually. The idea is that we simulated 1 million battles, so that we would never train it on the same exact turn of battle, ever. So one-shot learning, yes. Kalman filter, yes. I've implemented it, or I've been on a team that implemented it for anomaly detection before. Hoffman voting, no. I haven't done Hoffman voting. It sounds somewhat familiar, but I've never really taken a look at it. Naive Bayes, yes. I've implemented Naive Bayes from scratch in NumPy before. Also, I've got to take a quick break for like 10 to 15 minutes because my dinner is ready. But I'll be back in like 10 to 15 minutes. Hopefully these models are more trained and I'll be able to move on to the next thing. But alright, yeah, thanks for chatting. I need to eat dinner, so by the time I'm back you might be gone, but I'll be back in like 15 minutes. Thanks for the follow, I really appreciate it. I'm almost to Twitch affiliate. I need now 14 or 15 more followers, and I'll be able to be a Twitch affiliate and do subs and all that. But I'll be right back. Thank you.
All right, let's bring that beat back.
Okay, I am back. Okay, the results are getting better. Steadily getting better. The training loss is still pretty high, but it is much better than our previous. So let's look at scikit-learn saving and loading models, because that's something that we're going to do instead of Keras loading a model, but saving the model. Keras, or not Keras, sklearn save model. Wow. Other than Pickle, they don't really do a whole lot. That's strange. There's no just default library. I guess we just Pickle it. Okay. I guess we'll use joblib. That's fine. How much data are we at right now? We are at 65 batches done. Okay. I'm gonna move this. I'm gonna clean up the visuals a little bit and move some tabs around. Let's get rid of a lot of these other things. Model persistence, I'm going to move over. Okay, this is our gradient boosting regressor. We've still got plenty of CPU to train. So let's go back to gradient boosting regressor and let's try the hist gradient boost regressor. Okay, so this is much faster for gradient for big data sets. Maybe that's worthwhile. So let's go ahead and duplicate this thing again. We're going to copy 2, and this is where we're going to be using hist gradient boosting regressor. Does it have an end jobs thing? It does not. So we'll just get it running on exactly the same information. With exactly the same file. Ooh, n estimators is not a keyword argument. I suppose it doesn't ask for a number of regressors? That's interesting. Or a number of estimators? We could give these validation data as well. That would be good to do. But I think it's fine for now. So I guess it doesn't ask for a number of estimators, which is interesting. But gradient boosting does. Okay, let's just try it. It also has verbosity, so we'll see if it's gonna go faster. And it doesn't have end jobs, does it? No. Okay, that's fine with me. So that will run, and that will take its sweet time to print anything. So in order, we've got random forest running, which takes plenty of time. We've got gradient boosted decision trees running, which again takes its own time. It's down to like 628 loss. So less than 2/3 of our all zero issue. And now we've got this histogram gradient boosting regressor thing getting started. Additionally, in the background, we've also got more and more data getting generated so that our neural network can be working. I guess what we could do is we could also just start the neural network in the background and just go full everything running on my machine. How much memory is being used on my machine right now? A lot, but oh, that's because the simulation model trainer is still running in the background, or it's allocated that memory. Yeah. So that memory was allocated this whole time. I can actually be training this model too. So why not? So this is going to be model 1024 with all regulars. We need to do some sort of principal component analysis or something on this so that it can learn to use all of these different columns. We really need to do something like that because otherwise it's not going to be good enough. But oh well. And right now it's set to do early stopping after, we'll say, 20 epochs of patience. The advantage of this is that this checkpointing system allows it to save models periodically, so we can actually monitor how it's doing and even play Pokemon Showdown games against it, which is nice. I'm also going to just temporarily copy out this TensorBoard thing, because it seems like a lot of what we're going to do is not using TensorBoard. So I'm gonna... I don't have TensorBoard even running anymore. Okay, that's good. Okay, so let's run this. It'll do model checkpointing and a patience of 20. And right now, with how many files we're at, that's like 66 files. So that's 6.6 million turns of data. So let's run that too. Got lots and lots of models running all the time. I'm going to rename this one to be Random Forest. This one I'm going to rename to be Gradient Boosted. This one I will rename to be Histogram Gradient Boosted. And there we go. Binning 8.1 gigs of training data. Right. It's a good thing we've got lots of memory. One file is 8.1 gigs of training data. That's crazy. Like, all of these classical machine learning models are using... Ooh. Add got an unexpected thing, input shape. Oh, I've got the input shape copied in the wrong part. Let's see. There. Name error. TensorBoard is not defined. Oh, I need to remove it from the callbacks. There we go. It's removed from the callbacks too. So this is where having a workstation really comes in handy. We're finally using this computer for what it was built to do. It's at 70% CPU usage. We are streaming. We are training a neural network. We're training 3 different decision forest type models. And we've still got half of our memory unused. So this is what this machine is built for. And it's finally getting to stretch its legs a little bit. How are our temps doing? Perfectly fine. 55. That's perfectly good. Unfortunately, our neural network pipeline is a little bit limited by the file I/O. We need to find a better format for reading the files into a TensorFlow dataset. Because as it is right now, the formatting is horribly bottlenecked. Like the training of this takes seconds once it's loaded the data, but the loading the data is so slow that it ends up taking minutes to run a single epoch, which is really bad. Okay, Random Forest still running. Gradient boosted, still running. It's been a couple of minutes and it still hasn't given us another update. Histogram gradient boosted. Oh, it's actually giving us information now. Ooh, that validation loss is that training loss and validation loss is way smaller. This seems like a really good candidate. So this seems pretty decent. Nice. So by default, it's going to do 100 iterations of boosting, but we'll see if it's like stops improving. Nice. This looks like it's gonna be the method. It's way faster. It's actually giving us results. This just kind of stopped after a while. Random Forest also stopped after a while, but we'll see. This is going to a max depth of 50, so this has potential though to be really good. Whereas these ones are max depth of 20. But this is running pretty quickly, so maybe we could even step up the max depth. Because it's not taking that long. It took a little bit to bin the data, but we could even read in a couple more files because I do have plenty of overhead memory still available. Like I could read in a total of 10 files and it would have maybe 80 gigs of training data then. And that would be perfectly fine because we have the available overhead. The validation loss still decreasing. Now, if only we could do checkpointing with histogram gradient boosted trees. If we could do checkpointing, that would be interesting to do. Because then we could see it actually getting better over time. But I think once this finishes, we'll try it out and see, or we'll do some basic exploratory data analysis to see, you know, hey, is it actually looking right? Is it checking out? And if it is, then by all means, let's play it. Okay, so that was its 100 epochs. It had continued to improve though. It finished everything though. So okay, and at the end it ended up with 750. Wow. So it ended up still, the validation loss here and the validation loss here are really different though. I'm not sure why that is. I don't know why the loss is so different. Because we had some promise. Like 423 is very different. Maybe the loss is a different loss function by default. It says default is squared error. So I'm not sure why. Oh, it's half least squares loss. it's cut in half. Does that make full sense based off of our information? 423? No, that doesn't quite make sense. Oh, but this does. If we look up half mean square error, it is just divided by 2. And they use... What is the default validation? 0.1. So if we were to do 0.1 times 423 times 2 plus 0.9 times 369 times 2. Yep, there we go. Okay, so this number is actually half. That's a little bit of a shame. That's a little annoying. And it spent 5 minutes computing histograms, 5 seconds finding the best splits, and it fit all of the trees in about 10 minutes. Okay, so let's try this again. And now instead of just having it do 100 iterations, what we're gonna do is we're gonna say max iter. We're gonna let it go as long as it wants. Can we just say none? Okay, we can't. We can't just say none. But like, I want to just rely on the auto stopping. And what we're gonna do is n iter no change. Yeah, sure. 10 is still fine. Because I think if it stops for 10, that's enough. Validation for fraction, I'll shrink. I'll say validation fraction is equal to 0.00 or 0.01 instead of 10. So it's just gonna be 1% of the data because we've got a lot of data. So, and the max depth is gonna be 50. And so the difference here now is we're gonna use 10 files. Restart and run all cells. We got to like 700 something there for the loss. So we'll see how it is able to handle 10 files this time, and it can train as long as it likes with a much deeper maximum depth. And we'll see where does that get us in terms of performance. It will increase our memory size significantly. But that's okay. I don't think we'll run out of memory, but we'll see. If we do run out of memory, I'll step it down to maybe 8 files or 7 files. Depends. I'm watching the paged pool to see. Oh, we might run out of memory. Paged pool hasn't started increasing. It's going a little bit steady. The paged pool hasn't increased. This might be the limit. 10 files might be the limit. Oh, our random forest finished. Okay, random forest finished with a score of 408. Now, what we need to really do, though, is check how it does on a different file, because this trained on the whole file. So what we'll do is, instead we'll actually go from 1 to 2. So we'll run this again. Eesh. That stepped our memory up. I'll run that again. Okay. I'll predict it. So right now, 408 on the data it was trained on. And on new data, 927. Yeah, it overfit like crazy. So it had a crazy amount of overfitting. So random forest overfit to the data too much. So we'd have to train it on more data, or with more estimators or something to try to, or find something to reduce that problem. But we can clear out the memory because clearly 927 on untrained on data is really bad. Okay, gradient boosted. We really should have done... Okay, it's just stuck. It's clearly just stuck. I'm gonna restart this one. That way we can give it the better parameters. Because I want to give it... what did I want to give it? Where is it? Validation set? Validation fraction, there it is. Oh, the default is 0.1. Oh, only used if n iter no change. Where's n iter no change? Just blind. Oh, it was right next to it. So I'll do the same and iter no change. That way we can compare it. N iter no change is again going to be 10. Is there a max iterations? Probably. Maybe not. There's max depth. Okay, I guess that's fine. Just we'll say n iter no change equals 10. And that's good enough for me. So then we'll just stick with the same kind of parameters here, which gave us a max depth of 50. Validation fraction of 0.01. That's because we're using 10 times as much data for this one, because it's better for that. And here we're going to use a max depth of 50. Gradient boosted some trees. The default n estimators is 100, so we'll restart and run all cells here. It might briefly increase our memory usage, but it should be fine. Yeah, it decreases and then increases our memory usage. But it should basically go back to how it was just 30 seconds ago. Yeah, and clearly random was not the one to do, because on a new set of data, it just had horrible results. So I'm going to close it. How's this doing? Yeah, the loss here is still even worse though. We'll just let it run. It takes much longer, but the theory is that this could be the best if we just give it time. Our CPU usage has dropped tremendously because we're no longer training that random forest model, but our memory is just about full, so I don't think it makes sense to try to train it again during this. Histogram is taking a while, but that's because the first thing it was doing is splitting the data. I guess I'll get it set up so we can play with sklearn gradient boosting checkpoint. Warm start. Okay, so that's what they do. They use warm start in order to reload the data over and over again and dump things out repeatedly. Do the other things support warm start? Okay, so this has warm start support. What about this one? This one also has warm start. Okay. So that could be a way of doing it. Unfortunately, that would mean not training it on all the data at once, but maybe that's just kind of a better thing to do. In the end, this is 1, 2, 3, 4, 5, 6. So, yeah. This is 1 million rows of data it's getting trained on. We could train it on 100,000 at a time. Because that only took 5 minutes to load, and then 10 minutes to train for 100 iterations. Okay, I'm weighing the options. Gradient boosting regressor just... I don't know if it's a Jupyter Notebooks thing or what, but it's just not wanting to print anything. Okay, so this has support for categorical features too, right off the bat. That would be not a bad idea to use, but we'd have to reconstruct our data, which would be really annoying to do. Okay, so this uses OpenMP based parallelism. Ah, I see. It uses OMP num threads. So we might want to step up the number of threads it gets to use. Because right now it's just using 4. Now, this task, for all I know, might be a single-threaded task. I don't really know. Can we see what CPU usage? Okay, so the one that's using a crazy amount is using 2.9 to 3.5%. If we check that, we can see that 0.03 times 48 is 1.44. Okay, so maybe it's using more than one core. I'm not really sure, because 100% CPU is all 48 threads being used. It's also using 180 gigs of RAM. That's crazy. I think it's single-threaded though, because that's certainly not 4 cores. Because 4 cores would be 112, which would be like 8%. Unless they're shared. Okay, I'm gonna stop this, and I'm gonna stop the gradient boosting. Both of them. Okay, they're both stopped. Did this finally print, or did it just print as soon as I hit stop? Okay, so let's grab this environment variable. Environment variables. I'm going to pull this over to another page just in case there's anything that would not be a wise thing to share. And this uses the environment variable OMP num threads. OMP num threads, I'm going to give it 12. That, I think, is a wiser decision. If I pull up Task Manager, we can see we're back to having plenty of memory usage. So I'm going to try the histogram gradient boosted thing again. But this time what I'm going to do is, instead of doing it on 10 files all at once, what we're going to do is we're going to try this checkpointing method. That way we can be checkpointing it over time. So I'm going to cut this out, and I'm going to paste this right here. I'm going to get rid of the TQDM. And instead of doing 60 files, I'm going to do 50 files. So first what we do is we read the feather file. We pull out the X and Y from the feather file. We need to create this histogram boosting regressor out here. We step the validation fraction back up, the max iters back up to, let's say 50. So a smaller amount of max iterations. And most importantly, we need to say warm start is equal to true. We can get rid of this random state thing. And then we just say regressor.fit xy. And then with open, we're going to say for E, or no, we're not even going to save the checkpoint number. We're just going to save it. With open histogram gradient model dot p f, we're going to dump the regressor to F. Let's add some progress stuff. So we're going to say print reading file F. Should we have a complete validation set? Probably. We should probably have a complete one. So our val df is going to be pd.read feather, and we're going to tell it to read feather 0. Which is, let me get the exact file name of it. Batch0.feather. This file is going to use entirely for validation, and then we're going to say val x, or we'll say this is the test one. Other ones are validation. This is test. Test x is equal to test df dot I lock all rows up to -1. Test y is just the last one. There we go. Print fitting regressor to batch of data. This is going to fit the regressor. Then what we need to do is we need to score the regressor. So we'll just say something like test loss is going to be equal to test y minus regr.predict test x squared dot mean. So that's mean squared error. And then we'll print add test loss of test loss and we'll add an edge case of if it just stops improving, to stop having it waste all of our resources in the background. Yeah, so maybe we do want the batch number. And we'll say we'll go from 1 to 50 instead, because we want to keep batch 0 as our test. And we don't need to keep each one. We'll just say if, we'll say like something like results, history, is equal to that. We'll do results, history dot append, e test loss. That way we can graph it afterwards. And if test loss, you know what, for now we're not going to do any sort of interrupts. That's fine. If we want to like leave it overnight training or like over multiple days training, we could do some sort of interrupt, but I think for now it's fine. It'll just go through all 50. Sure. Okay, so that lets us do checkpointing, which is very important. Oh, I don't know why I have print in capital letters right there. That's gonna annoy me. I'm gonna stop and restart this. Okay, now I'm gonna run it again. All right. So now this will be running it and saving it as a checkpoint each time. So then we can actually, as it's training, load the model and play a game against it and see how it is at this point. What the heck? I have plenty of storage space. I'll have it just save a different file every time. There. That way, if it gets horribly overfit, we can go back and get an older one and use that instead. Okay. So that's training. How's our neural network doing? It's come down a little bit. I think the neural network approach, in theory, will work. But I think the issue is that in practice, it's so many weights, because there are so many possibilities, that it will take weeks of training time for it to drop in its loss. Now, I'm hoping that I'm proven wrong. I'm hoping that after a certain point, it just kind of gets the ball rolling and improves faster. But this has been running for like, and it is technically improving each time, right? Like each validation loss, one after another, is decreased. It's just really slowly decreasing. So maybe it'll get the ball rolling and it'll be improving faster each time, but I'm not super hopeful for it, which is why we're working on other alternative methods. Okay, so this is working. After it saves one checkpoint, we'll load it and play against it, because already it'll be better than the neural network one. Gradient boosted, let's copy our code here, because now all we're gonna do is repeat the exact same thing, but with the gradient boosted approach. So I'm going to cut each of these and paste it here. But now instead of hist gradient booster, we're using gradient booster. It doesn't ask for a max iter. And we do need to give early stopping as an information. We need to give n iter no change to be 10 so that it'll do early stopping. N iter no change being 10 is the same as with the histogram, so it's got like the same parameters as with the histogram. Good, good, good. And I think basically that's it. We'll just have to change the name of the model and restart run all cells. So now our memory usage is much slower, which maybe is inefficient, but I think some of the processing is single-threaded. So we weren't actually taking advantage of loading more data into memory. So I think it's probably actually better for us to be running multiple simulations at the same time with different models than it is to just run one model on more data. I think that kind of makes sense. It checks out from the sanity check perspective. And on the bright side, since these are training on smaller amounts of data, in theory we should start getting checkpoints faster so we can start loading them faster. Okay, so there's our hist gradient boosting regressor. Hist gradient boosting regressor. That's a mouthful to say. And now we can try doing our random forest one as well. Though the random forest had a really large overfitting problem, but maybe with us operating over more files, it won't have that huge of an issue. Okay, so that's training. It takes a while to print anything though. Histogram regressor was much faster to print. It's a lot more verbose, which I like. Also, an important thing, the loss here is half mean squared error, so you actually double it to get your real mean squared error. But these will run for 50 iterations, save a checkpoint, load the next file, run for 50 iterations, etc. Is our max depth still 20? No, we set it to 50. So in theory, it should be able to go all the way up to 50 max depth. All right, so that's running, which means actually in a couple of minutes, we'll have a checkpoint and we can load it and play Pokemon against it. So if you're watching, we're right now creating a bunch of different models that are all plug and play. They're doing exactly the same thing in terms of input and output, and we've already got the full framework working for playing against the models. So as soon as a model is saved, we can load it in and play it in Pokemon Showdown. So if you're watching and you want to try playing against the AI in Showdown, we can set it up and it'll be no problem. As soon as one of these models is saved to checkpoint, which this is halfway through the first round of training, so it'll be pretty soon. We've also got the baseline model, which is terrible, so we can play that, but I think it's worth waiting just a little bit for this, which is a little bit less terrible. Oh, my bitrate has dropped. I'll be right back if I'm still technically streaming. I'm going to plug in an Ethernet cord. I'm plugging in an Ethernet cord. I'll be right back. Okay, I am back now. Hopefully my bitrate will be a little bit more stabilized. I noticed that it was buffering like crazy on my preview window, and it showed that I was at 300 kilobit per second. So I plugged in an Ethernet cord. Unfortunately, there's no in-home Ethernet here, so I just roll it all the way down. Oh, right as soon as it was about to save, it failed because Pickle's not imported. Dang it. Okay, let's stop the other one and... This still never is getting to the point of training. I wonder if we need to train this on even smaller batches. This might need to be trained on smaller batches. So let's do for for B in range df.shape 0 divided by, I don't know, 10 batches? Wait, no, this is the other way around. I want to have each piece be maybe 10,000. Then what we're going to do is we're going to say, we're going to cut this, paste it here. I'm going to make this no longer verbose. While we're testing it, it'll be verbose. It'll print a lot to the log, but I think it's worth it. And it's going to train it on each individual piece, and it's going to be B times this whole thing. Or no, B times 10,000. 2 B plus 1 times 10,000. And then the same with Y. There. So now it's going to train on smaller batches at a time, and hopefully that will help speed up the gradient boosting regressor. The histogram one seems to not really have this issue. I think because the hint is in the name that the histogram regressor is not using individual samples to make decisions. It's using the distribution of the column itself to make cuts. And so it doesn't really need to look at every single thing individually. Okay. That's a shame. We were so close to getting something a little bit more fun. And so this will run on still one file at a time before it checkpoints. So it'll do 10 rounds of training, then do a checkpoint. Whereas this one will do 1 round of training, but it's because it's seeing 10 times as much data. So it makes sense. Oh, even still, the gradient boosting tree processing is still slow. Is there any way of speeding it up? Because that is painfully slow. On this pace, it would be 10 hours for 1 checkpoint. And that's a lot of iterations for 1 checkpoint. Or that's a lot of time for 1 checkpoint. If it takes an hour, it's saying its remaining time is 1 hour. Let's zoom in a little bit more so it's clear. Like 55 minutes to finish off the training of just this one. Now, the training loss is dropping pretty quickly. Our histogram stuff, this is half mean squared error, so it's actually higher. It's tricky. It doesn't seem to be that painfully slow. Maybe the end internode change will kick in, because each iteration is taking 30 seconds. So that's like 300 seconds. It's 5 minutes of not improving. So maybe that'll kick in, and then it'll end earlier instead of this remaining time estimate. I'm not sure how this remaining time estimate is calculated either. But we can just be hopeful that it does speed up. This process, on the other hand, it seems to print out different information in the log. But we can go ahead and estimate for ourselves. It's taking about 4 seconds. And it's got 25 more. So 100 seconds. It can process a lot more data in a faster time than the single gradient boosted thing. But this gradient boosted algorithm, while it's slower, seems to be doing a heck of a lot more to reduce the training loss. We'll have to see how they stack up on the test loss, though. Our test set is our first batch of data. Every other batch of data will be treated as training data. So we'll have a full 100,000 rows of data that it can test on. Yeah, we can already see that this is dropping off in terms of its decreases. At least this will checkpoint earlier, though. And 482 times 2 is just shy of 1,000, and our kind of bad number of what's just predicting 0 all the time is 1,000. So hopefully some of these algorithms can be better than that. I'm hopeful of this gradient boosted, because numbers as low as 300 for the loss is much lower. For reference, our neural network, it's dropped down more, 974. It's still on a generally downward trend. But this is after processing 1.1 million rows of data. It's at a loss of 974. Okay, so this had a test loss of 898. Okay, so it's about 100 better than our default. So that means it's about 10% better. So right now we've seen, after one iteration of this model, 10% improvement. Let's see what that looks like in terms of Pokemon. So what we're going to do, we do need to just swap it from using Keras to using scikit-learn model, but that is 2 minutes of effort. What it does is, instead of using self.model equals load model, we're going to say self.model is equal to pickle dot load open model path read bytes. Okay, so we're just replacing this line of code, and that's the only change we have to make. Because the rest of it, which is right here, self.model.predict, that will work exactly as we're needing it to. Okay, now let's just make sure that the test is giving it the right things. So instead of notebooks / model 512, we are going to use this checkpoint that we just saved. Which is histogram gradient model _0.p. And the whole file is pretty small, so it's not that bad. And we are going to use, instead of this label or instead of the label encoders that's out here. Oh, I deleted it already. We're going to use notebooks / label encoders. Oh, dropped a bottle cap. And here we're also going to use notebooks / histogram gradient model. There we go. So these are the right files. Let's say python test.py. Seems to be taking a little bit to get initialized, but not sure what it's waiting for. Oh, load takes exactly one positional oh, oops. I misplaced one of the arguments. This RB is supposed to be in here. Let's try that again. All right, so it's ready and waiting. So now what I'm gonna do is back over here, instead of just logs showing, training progress, we're gonna go to Pokemon Showdown. Let's go to play online. Let's go to find a user, Wander AI V1, and we are going to challenge Wander AI V1 to a Gen 5 random battle. Alright, let's look at the log. So it said that Fire Blast had a predicted move score of 3.79. Its other options I'm not sure of, but that's a Fire Blast against my Parasect. It's a pretty good idea. I wonder if we can... we should probably have printed, instead of all this log information, maybe we'll do that for a future battle. Moltres has Hidden Power, U-Turn, Roost, and Fire Blast. So we should edit the log so that it gives us a little bit more of a better idea of what the right move is. But I'm also going to minimize this so I'm not cheating. I already know its first move, but I probably wouldn't stay in anyways. So I'm going to switch into this again. Let's hit it Toxic. Okay, it used Fire Blast again. Now, we're still expecting it to be pretty bad, because this is the first checkpoint. Over here, it just saved a second checkpoint with still almost as bad a training loss. Oh wait, no. It hasn't done a second checkpoint yet. So let's protect. Let's just scout it out of Fire Blast. It's using Fire Blast repeatedly, which has the same score. So that means it hasn't learned much about, other alternative options or things to do. Let's just, I don't know, Seismic Toss. It's the first AI had the tendency to repeat moves over and over again, and this one seems to still be following the same tracks. Hopefully, once Gradient Boosted finishes and saves a checkpoint, which will probably be in about an hour, we'll be able to see if that's gonna have the same issues. As of right now, it's really hard to say, is it 10% better than what we had before? I don't know. We can say that its second best move is whatever this move is, which might be Roost, now that I think about it. It could be Hidden Power. but it might be Roost. We'll have to edit the log so it prints out something a little bit more friendly. I'm just gonna use Seismic Toss because I used Protect last time. Okay, it sent out a decent Pokemon, and it's gonna use a decent move. But I'm just gonna Toxic it again. We've got to let it train for longer so it can learn what to do. Right now it seems like what it's doing is it's just thinking better move is better, so just use strong moves. It's not using random moves, it's using strong moves, but we didn't program it to know what the power or types or anything of moves are. We just gave it an ID for what the move is and the training data, and it's learning. So, you know, it's not making wise decisions, but it's not making stupid decisions by any means. Like, it's not making just like random pointless decisions. It's just gonna keep repeating its strongest move though. So while these models are training in the background, it's important to think of what is it doing right now and what do we want to see it do less of. So right now it's just this choosing Aeroblast, choosing Aeroblast. You can kind of see it peeking out in the log down here that each time it's about to move, this is what move it's coming next. So I'm kind of cheating because I know what it's going to do, but just so you in the audience can see what it's doing, that's what's happening. Alright, and Lugia's out. Kangaskhan with a double edge. That could be really bad. But I'm going to pretend I don't know that, and I'm just going to protect like I would normally do when you're scouting out a move. Only a Toxic. Or maybe not. Jeez, that was a massive amount of damage. Protect. And then I know it's going for double edge. I can send in Ferrothorn. Oh, and if you in the audience want to play against the AI at any point, let me know in the chat, and we'll get it set up so you can play the AI. This is on Real Pokemon Showdown, and the AI is playing on Real Pokemon Showdown, so it's completely doable. You will have to have an account, but an account is free. I guess that's Leishi. Right now, clearly the AI isn't very good, but we've got 3 different models training in the background and saving checkpoints, so we can see it get better over time. Okay, so that's still running. I don't know. Let's also send out a Stealth Rock. I'm not very good at Pokemon, but I can at least beat this very dumb AI. The only issue is that the longer I drag out that, the higher it is a chance for my special defense to drop. Let's scout out a move, protect. It knows that Sucker Punch is a good move. I don't really have anything to counter it, either. Like, this team is really not too good of a team. Let's set up another Pokemon. Let's do Swords Dance Baton Pass to, do I have any physical attackers? Landorus is a physical attacker. Swords Dance. Is my attack maxed? Oh, yep, my attack was already maxed. Alright, and then Baton Pass to Landorus. And let's go for Earthquake. And then Earthquake again. Oh, it's got Levitate. Wow, that was almost real bad. As we use Superpower. Alright, and that's the game. So, model still training in the background. Let's get music back on. And we're at... Jeez. A lot of data. Batch 90, so 89 batches of data are done. So these models could just train basically in perpetuity. Up to like 1,000 batches or something. That one still has a while to go. Okay, the validation loss is coming down over time. I don't know why the training loss isn't. That's really weird to me. Because it shouldn't be seeing the validation data ever in training. So why is that? I don't know. But it's coming down pretty steadily, actually. Gradient boosted, still taking some time. Histogram gradient boosted, still taking some time. What's our memory usage and CPU usage? Okay, we can do the random one as well. So what we're gonna do is we're gonna open up Random Forest. We're gonna cut those. Accidentally hit Control C. I keep doing that. We're gonna paste this code, but swap out Hist gradient boosting with Random Forest, and now we're going to do instead of max iter, we do n jobs. We're gonna say n jobs is equal to 20. Random Forest doesn't take validation. Yeah, it doesn't take validation. So we get rid of that. But other than that, that's good. And then this is what it's going to do, is it's going to run on one file at a time, creating results. I'm going to shrink the max depth down to 20. And hopefully that will be good enough. And instead of histogram gradient model, it's going to be Random Forest model. And then we cut that cell. And now it looks just like the others. Except we need to make sure we import pickle this time. Otherwise we wait for a long time and then nothing happens. Oh, uh-oh. Our histogram gradient boosting doesn't seem to be working too well. The warm start isn't working. Shoot, let's stop it then. The warm starting isn't working. It's not doing it again. Let's see what this error is. X does not have valid feature names, but hist gradient boosting regressor was fitted with feature names. It's when it's predicting things right there. I'm not sure. This is not great. Let's see. Histogram gradient boosting. Histogram gradient boosting regressor. Warm start. I think warm start doesn't play too nice with the max iterations. Interesting. Which makes me a little bit worried for the gradient boosting. But we didn't set a max iteration here. What's the default max iterations? Is there one? Maybe we need to set it really high so that it just stops after it stops improving. Let's try that. Because maybe that's the cause of the warm start thing. Because it's training all 50 on the first file, and then it's giving up, I guess. We could also have just tried setting an iter to being 0 or something and see if that works. But I think this is a smarter approach anyways. So I'm going to delete the old model files. And our neural network one is still running. It's the rate of the improvement has dropped though. At least it's getting a little bit better. 959 is the best we've seen from the neural network method. If we could just get the data pipeline to be faster, this would be the way to go. But the data pipeline does not want to be fast, which just causes headaches upon headaches. Okay, that's running. MBS log parser is still running. Nothing super interesting happening on any of those. Can you have like a friends list in this? Because I'd want to kind of friend the AI so I could just send challenges. Yeah, let's go ahead and edit this code so it prints out a friendlier log. So what we'll do is here we'll set verbose to be false. And then what we'll do is we'll say for choice score in zip choices scores or choice scores if we need to import some typing stuff. So from pokenv.environment .pokemon import Pokemon, and then also from pokenv.environment.move import move. And then what we do here is just for friendly printing, we say if is instance choice a move print using move or choice had a score of predicted score of score, else print switching to choice had a predicted score. Okay, so what that'll do is that will give us some kind of more fun information about what the choices are without printing like a huge mess of stuff. My bitrate has dropped again. I don't know why. I'm connected over Ethernet now. My internet should be smoother, but my bitrate is still dropping. Not sure why. That's a shame. Hopefully it doesn't cause too much problems in the stream. Okay. So we've got it with our new and improved log. We're going to load it again. Did I delete the file? I did delete the file. Dang it. Do we have to wait until it saves a checkpoint again? Quite possibly. How long is that going to be? After it stops improving here. It's probably still in my trash. I'll just pull it out of the recycle bin. That's fine. There. I've recovered it from the trash. That's fine. It'll get overwritten by this. It's not a worry. Alright, and I'm gonna pause the music because Showdown's gonna have music. Let's go back to Pokemon Showdown. Challenge? Alright, here's our challenge. And now if we pull back up the log again, now it's got a lot more information. So now we can see that it has just a bunch of switching moves had bad moves, and then all of these had basically the same score. So this model is not very good. It knows that switching to Hariyama is a bad thing, I guess. Like, that had the worst option. It didn't want to switch to Hariyama. And then as for all of the moves, it's pretty neutral about it. So it just doesn't like switching right now. I think switching is a bad thing to do, which makes sense. You probably shouldn't just randomly switch. But then all of the moves, it doesn't care one way or another. So that's what we want to see change as we are loading these checkpoints of the models getting trained. That right now, it's all very, very similar, the scores. Like 0.21, 0.21, 0.21, 0.21. It's like practically the same for the model. In fact, this random forest probably is doing exactly the same for these moves because of the sheer number of the columns. Okay. So let's, we know it's going for rapid spin, but let's switch to something else, I guess. Because we can't really do much ourselves here. And we don't really even have any good switches. Wow, this team is garbage. Starmie, like, we don't have an answer to Starmie. I guess we can use Drill Run. Yeah, that's not gonna work. Let's switch to Mandibus. There's still a lot of warnings being printed, so we need to get rid of the warnings. That way the log won't be so useless. And again, the move stuff is not useful. Use Toxic. I guess we can use Foul Play, because I'm pretty sure it's Water Psychic, so... It's faster, so I'll just use Roost. Okay, so here it's using Baton Pass, but there's no reason why it should use Baton Pass. It's the moves that it's using are just not very good. Let's see why it decided to switch to Illumise. So in this case, it's just because it really didn't want to switch to Hariyama. That's why. It really didn't want to switch to Hariyama. But all the others were tied, just because it hasn't learned enough to be good at that. And it's right, Hariyama would be a bad switch, which is why it got a lower than typical score. But here, it probably should have switched to... I don't know, it doesn't really have all that many good switches either. Maybe Ho-Oh, or maybe Audino. To like try to Toxic it. But I'm just gonna... Oh, it used Brave Bird to Keldeo, which I just did a bunch of damage to. Oh, Scald. Oh. Uh-oh. It's... I'm gonna use Brave Bird again. I might get knocked out. Probably not get knocked out by Brave Bird, but... Its team is certainly better than my team. Oh, it used Substitute. That's wise of it to use Substitute. Oh, but it failed to use Substitute. Is it just going to keep using Substitute over and over again? I think so. Just like it's always going to switch to Illumise. Okay, it used Toxic back. I'm gonna use Roost. Yeah, it's just still thinking over and over again it needs to use Toxic. Are there any moves that would be good? Yeah, use Double Edge, why not? But it's tied, because it probably isn't considering that. So this is an issue with the decision trees. They're really bad at encoding one-hot encoded parameters, so maybe it would be worthwhile un-one-hot encoding those parameters. At least for the Decision Forest approaches, that maybe it would be better. Because otherwise it's just, it's not learning a lot of the options that it could be.